This afternoon is Alastair King, and the title is Preprojective Algebras and Quivers and CFT, preprojective algebras and beyond.
Okay, so thanks very much to Guy for giving me the opportunity to talk here. I think my role is largely expository. I will try to explain what an almost Calabi-Yau algebra is, for example, which is in the title of the meeting, so I guess someone should do that. And I also want to explain what this list of quivers is. And fortunately or unfortunately, fortunately, the top line already appeared at the end of Osama's talk, so that was very well organized of him. So I want to start by saying a little bit about the appearance of quivers in conformal field theory, but only in the very simplest of cases, which is the SU2 level case. Working model. So this SU2 is going to very much correspond to the sort of classical case, and then SU3, which is what this picture is for, will be the beginning of the moving towards the higher case. So for an algebraist, I don't really understand what a CFT is, although I have seen kind of books about it, but the sort of algebraic ingredients at least. So let me mention three things. Firstly, there's some category of irreducible representations of some chiral algebra, or vertex operator algebra, as James explained yesterday. In this case, say this is spanned by, the representations. The representations of the chiral algebra is a semi-simple category. It's spanned by the simple, something called V0 up to V K. That's the K. It's a tensor category, so it's tensor generated. In this case, just by V1, and it has SU2 fusion in the sense that, well, this is the limited, in larger sense than this, but let me just, for the sake of current purposes, I would like to say this means that V1 tensor Vi is Vi minus 1 plus Vi plus 1. Okay, and this is truncated in the sense that if you end up trying to write down something which doesn't appear in this list, that's 0. So, this is typical of, say, the bottom of the list. There is no V minus 1. In this particular case, there's also no V K plus 1. So this is really truncated SU2 fusion, truncated at level K. Okay, and we can write down fusion graph for this. Maybe I'll use the labels 1 up to K. Simply, what happens when we tensor any one of these simples by V1, and what are the factors we get? So tensoring 1 gives 0 plus 2, tensoring 0 gives 1, and then it continues. So we end up with a graph, an oriented graph, which, as it seems to happen in this case, actually is the double quiver for an AN quiver. Now, at the moment, this is really just a graph. It's just an oriented graph. But if it's going to be a quiver, then, as we saw in Simon's talk again, we really want to do some sort of representation theory with it. We want to turn it into a more linear algebra object. That might mean we simply want to try to represent the quiver by vector spaces and linear maps. Or it might mean that when I draw this picture, I would like you to see a semi-simple algebra, somehow spanned by idempotencies, one for each vertex, and a bimodule spanned by the arrows. But at the moment it really is just a graph, so it's something which could become a quiver later. Okay, and then two particular sort of things in this category, or almost in this category, that are apparently relevant are somehow a Hilbert space associated to a closed string. Well, I don't have to really understand what that should mean, but which is a direct sum with certain multiplicities of VI. Somehow there are two copies of the current algebra here, so we denote left and right moving, we denote the other one with a bar, and then this thing is the famous modular invariant, which is part of the data which builds the full CFT. And then somehow what I'm going to more focus on is a sort of open string story that really puts boundary conditions into this conformal field theory. So if I'm supposed to imagine, say, an open string, some interval going between boundary conditions A and B, then I'm supposed to see some Hilbert space. Another Hilbert space, which now is just a direct sum. This is genuinely maybe some multiplicities, I'll call NI AB, BI. So this is some, not reproducible, some representation of the specific representation of one copy of current algebra. And in this case, for this famous classification, we've got enriched somehow as well, but by Kelly, Isaacs, and Zubair, says that such things are classified by ADE Dinkin diagrams. Okay, and what's the relationship between the Dinkin diagram and any of this data? Well, I guess the first thing we say is that the level K is 2 less than the cox of the number of the Dinkin diagram. Secondly, and I guess kind of historically, this is how these letters got attached. Originally is that the modular invariants are characterized by the diagonal terms being non-zero when I plus 1 is a so-called Coxeter exponent. And that was really the first clue that these Dinkin diagrams were involved. So these Coxeter exponents essentially tell you which powers of e to the pi I over h appear as eigenvalues of the adjacency matrix of the graph. That's a pretty strong clue. And then really the kind of overwhelming thing at the end is that these boundary conditions can be identified with the vertices of the diagram, delta 0, just write subscript 0 to denote vertices, and the direct sum over all boundary conditions of this ABI is the ith graded piece of the preprojective algebra of delta. I should say two things here. Firstly, someone described a grading of a preprojective algebra which depends on a choice of orientation of the quiver. This is not that grading. This is the more naive grading, which simply says that all the arrows here have degree 1. And secondly, as he mentioned very briefly at the end, I mean, this orientation in this case is like a choice of cut. And in fact, different orientations will give you the same, in this case, the same preprojective algebra, or strictly isomorphic preprojective algebras.
So n is not a number then? NIAB is
it's a vector space.
vector.
Yeah, I mean, not being little stop. When I write this, really, this is a multiplicity space for a representation. It's this
The
vector
product
space.
is the tensor product.
There's lots of tensor products in here. Yes. Or it could be a number. I mean, it could be the dimension of it. It could be the dimension of this space if you want to think of it as a number. This is just some sort of, yeah. Okay, and one in particular, it is known that as someone said, the preprojective algebra in this case is finite dimensional. In particular, it has a top degree, and the top degree in this case, as it would have to be, is indeed h minus 2, i.e. the value of k. So when you first see this, which I guess I did 15 years ago or so, it's quite striking, and you want to know why. Why is it that these numbers are numbers that all representation theorists know?
Is it visible that this direct sum of NABI admits an algebra structure?
Yes, that's essentially one of the things I'll try to draw out. You mean, is it visible on the CFT side?
Yeah.
I guess you have to ask the CFT person. But I guess the answer is yes, for reasons which hopefully will become more apparent, maybe even now. So the point of view of principally, I guess, Ostrich and others is to say that, well, there's another way of saying what's going on here, which is that there is a certain, well, if this category C, because it's a tensor category, is a sort of ring category, so we should ask, what does a module category, not as in the category of modules, but a category which is a module for this ring, look like? And the answer is, so we can interpret this story in those terms. So I can write down, indeed I can now start to think of a quiver. I can write down a set of idempotents, so the idempotents of the vertices of this quiver, of this diagram. And I have a semi-simple algebra, and I can think of a representation f of C inside the category of SS by modules. So let's say this is, if we have a quiver whose vertices are labeled by the vertices of this graph, then something like the span of the arrows is exactly an example of such an SS by module.
What is C?
Oh. C is this category of representation. But I think of SS bimodules as really endofunctors of the category of S modules, just acting by tensor product. So this is, if this is a ring, then this is a module for that ring. But I'll explicitly write everything in terms of SS bimodules, and these objects VI now should map to pi. And the dimensions of these pi i's can be thought of as matrices. Each of this as an SS phi module has a component, as an AB component like this, so these can be thought of as matrices, or the dimensions can be thought of as matrices. And this then, one consequence of this, which can be used to kind of find these, is that this is a representation of the SU2 fusion rules by non-negative integer matrices. A non-negative integer matrix representation. But this is a sort of a categorification of that story. And then, of course, in particular, this should be a monoidal functor, so V naught should go to, which is the identity in this tensor category should go to S, and V1 should go to what I'm going to call, so this is just the degree 0 part of I naught, as I said, this is the span of the vertices, and then the thing I've called X, which is the degree 1 part of that, which is the case linear span arrows. They go away, delta bar 1. So the quiver you make from the Dinkin diagram by putting in arrows and going in both directions. Okay, and in particular, we know from the, I guess by analogy with SU2 fusion, we know that there is actually an interesting algebra object in C, which is just the direct sum of all these simple guys. There is a multiplication. Vi plus j occurs as a summand of Vi tensor Vj, so we can make a multiplication on this, which I suppose you might want to call some quantum version of the polynomial coordinate ring of the plane. Here, so this is some algebra object here, and that maps over to the preprojective algebra pi. So, and then possibly the other comment we want to make is that type A is what you might call the regular representation. This is a ring. C will have one candidate for S mod would actually be C itself, and in that case you actually would end up with the preprojective algebra of type A. So it's sort of no longer a coincidence that this fusion graph actually is the double quiver of type A.
Sorry, did you say that sigma is an algebra object?
So sigma is an algebra object inside C. So just in the usual way that the sum of all the irreducibles of SU2 is the polynomial ring.
Isn't it supposed to be tensor with its conjugate?
There's no conjugate.
Well, what's the algebra structure?
But the algebra structure just comes from the fact that Vi tensor Vj has a summand, and so a map onto it. Then you have to check that that's associative. You think it's not? Okay. In that case, this is possibly a technical point that has to be.
Well, if you take the representations of a finite group and take the direct sum, is that an algebra?
I'm not saying this in very generality. I'm just saying in this particular case. I mean, this isn't a property that C has just as a random thing, but it is a property that it has in this case. I would claim. If it doesn't, then okay, something needs to be. There is something in it that needs to be fixed. This is kind of an important feat.
No canonical map.
Okay, so I mean, of course, at the moment I've just said this is, Ostrow's interpretation is that this should be true, but how would we go about seeing that something like this was true? Well, we look at a sort of diagram. Realization of C, which we've heard about, at least implicitly, because there already. We write down the category, the temporally lead category, whose objects look like some finite collection of dots on an interval, and these morphisms look like isotopic classes of ways of joining up the dots. So this is, say, a map from, I call this N, loosely speaking. I was trying to be more careful, perhaps. I mean, there are lots of isomorphic objects, all called N. I'll go over that for a moment. And then we compose in the standard way by concatenation. We end up with things that are like this. This, because this should be, this is isotopic to that, so this should be equal. The identity of 1 for 1, and then we impose one relation which says this picture of a closed loop should be minus quantum 2 times the identity for the zero object. Just has no picture. So this was the relation that Gus went down. And of course, the case Q equals 1 just gives the standard diagram calculus for recovering the representation theory of SU2 itself, but the case we're particularly interested in here is that when Q is a primitive even root of unity, there's a small technical point that we really do want to be an even root of unity to make C actually a richer thing, to make C a modulative category rather than just. I don't dwell on that either. But so in this case, TL itself is not semi-simple. Essentially, as we've been told already, although I mean, this is a statement about the category itself rather than the individual algebras. But there is a semi-simple quotient category which I'll call TL tilde, which is just category divided by the idempotent. So in this case, this is sort of the last Jones-Menzel idempotent, the last definable one in this context. And then we can say that C is the, this is equivalent to the idempotent completion. Tilde. But somehow taking a Uneda point of view, given this is going to be semi-simple, I'd like to really rather think of this as actually just the category of representations here. So by that I mean be careful, contravariant functions to vector space. Okay, and then this object V, the object VI, formally is thought of as the object I in TL together with the corresponding universal idempotent, but really it corresponds to something for to avoid confusion. I'll distinguish from it is the functor augmented VI on this category. So this is a in some sense a more concrete set of thing than the idempotent completion, and this is potentially a more concrete functor. Even if I didn't know what VI was, I could still write down what this functor is, essentially using the idempotent. So this is a sort of, in some ways, a slightly more concrete way.
Is it here Chirada semi-simple?
Yes. Yeah, TL filter is semi-simple, so yeah, it's crucial, but otherwise you wouldn't have this. Okay, and now we want, well, what do we want to know about f? It will be enough to have, to write down a functor from TL tilde to S modules, SS bimodules, sorry, which again will take 0 to S. It will take 1 now to X, what it was before the span of the arrows of the double quiver. And then, of course, it will just take N now to be a tensor functor to X tensored over S n times, which we can identify with paths of length n on this double quiver associated with the Dinkin diagram. Okay, and the point is we'd like to actually make this into a functor. So in this case, in this context, we have to really say what these two diagrams are. So this diagram should be a map from S to X tensor X, and to a first approximation, this is exactly the preprojective relation. So we can think of this as a single thing in some sense, or we can think of this as a relation for each vertex in exactly the way that someone explained. And then, but we also need the other diagram, whichever of these is a cup, which is, roughly speaking, complementary projection. Okay, but this is not quite right. So to actually get the relations to work, both of these have to be weighted by an eigenvector of the adjacency matrix with eigenvalue minus 2q. So this is the technical point that really tells us what Q has to be in this case. In fact, so this is to get basically the two pictures that I wrote up at the top to come out right. So it's not quite, there's two things here. It's not quite the preprojective relations. We have to weight them a little carefully, and we also have to have a projection, a complementary projection. Okay, but then we can essentially prove, we can essentially see that then VI's, okay, to the extent that they are not elements of TL completion, the VI's will then map to the ith component of the preprojective algebra, but now actually really as a summand of paths of length n, not just a quotient of paths of length n. And these are, so then these are kind of being really realized as essential paths, which was the way Anu first described this story. But one may also describe this in a slightly different way, or and alternatively, if we simply think of the functor which counts instead of all paths, just paths. Oh, the other thing I wanted to say here, yes, of course, is that I mean, not only do we have to have this working, but we also have to see that this functor does actually really pass to TL tilde, which means it really does vanish on this last idempotent ES1, and it does. And somehow, because this is coming about, somehow partly because of the way the preprojective algebra does cut off at H-2. Okay, so another way of describing what's happening here then is to say that we have this functor which simply counts paths from A to B, and formally, I mean, as a functor, FAB is the direct sum. Okay. Then B phi in red TL tilde. So I also find this a bit striking, although I don't quite know what necessarily wants to do with it. But we now have a situation where we have something, this category TL, inside this category of representations we have a particular functor, just this simple path functor, and it decomposes in exactly the way the boundary Hilbert space is supposed to decompose into the simples. Conceivably, if you had a way of taking some limit, this formula would become that other formula in the limit. But you might also consider this formula is on its own a good enough reflection of that thing.
So how, I don't understand how FAB is defined in this context.
FAB is simply the functor which takes an object n in here to the paths of length n from A to B on this double quiver. And that functor has a decomposition in terms of simple functors, and these things are the multiplicity.
Oh, I see.
I mean, this was effectively often known as original observation, that these multiplicities count essential paths from A to B of length I.
Are those coefficients related to the dimensions of the graded components of the preprojective algebra?
Yes. Yes, this is the NIMRAP. If you think of these as SS modules or their dimensions as matrices, these are exactly the NIMRAP. That's what I'm just rubbing off. So in some sense, this is the explanation of why the dimensions of the preprojective algebra appear as multiplicities in those representations, because this formula is a mirror of that. I mean, this is sort of the beauty of Ostrich, the module category point of view. Okay, so we've heard a little bit about why these algebras are special, both from Summer and from Karen. So I want to try to explain how this can be thought of as coming about directly related to SU2 fusion. Now, if you insist that these things aren't algebras in C, then I'm going to want to, this may need a bit of fixing, because what I want to say, if you want to repeat, is that this thing is a graded algebra in C. I want to consider another object lambda, which is in some sense equal to this, which is, okay, just has 3 degrees, 0, 1, 2. This is lambda 2, but it's V0. Again, and this is a graded co-algebra in C. And the only interesting sort of map here is lambda 1, so lambda 2 mapping to lambda 1. And so lambda 1, which in this case is exactly this guy, the guy that essentially is the preprojective relation. So this co-algebra, amongst other things, encodes the relations that determine this algebra. Okay, and now we can think about what SU2 fusion tells us as being that there is a short exact sequence this form. So SU2 fusion says this tensor product decomposes into the sum of this guy. I mean, this is sort of trivial, but I'll write it there, plus this guy. So this is actually a split. For the exact sequence, at least for 0 is less than n is less than h. So at the bottom, this can't quite be true because both of these terms are 0, and this thing is not. And at the top also, this can't quite be true because both of these terms are 0, and this one is not. But apart from those two cases, this essentially is the SU2 fusion rule. This is the SU2 fusion rule. Okay, well, if we sort of add all of these up, we can then get, this gives almost what we would want to call the causal resolution of the simple guy, B0, free resolution. Except there's a third syzygy here, and this syzygy is just under 2 centimeters. So something in degree h.
And this sequence is exact?
This sequence is exact. Ideally, we would prefer this was not there. This would then be a free resolution of V, and this would be the causal resolution, and this would tell us that sigma was a algebra with lambda as its dual. And in fact, so because this is only almost true, we say sigma is almost causal. And indeed, almost, in this case, almost 2 Calabi-Yau. So this 2 Calabi-Yau property, in this case, comes from the fact that this lambda is isomorphic to its dual, restricted by 2. So lambda is self-dual, but only with a shift. Here. So this is the sense in which, I mean, the SU2 fusion is very much what's behind So because this is simple, in some sense what we now have is the building block to build a periodic resolution of the sort that Karen was describing before, but now I'm just doing it all inside this category C, hopefully. But we can get back into kind of the real world, in some sense, by applying F to get the preprojective algebra itself, which is F of sigma, is almost 2 Calabi-Yau, almost zero. F of lambda, or possibly you might prefer to write down the algebra, which is dual to that's what would be called the trivial extension algebra. So this is sort of known already in the context of representation theory. I should say that somehow all of if we hadn't started with a Dickian diagram, and we started with a more general graph, a lot of what all these constructions would still work. We still have a functor. Only in that case, the relevant value of Q would not be a root of unity. The maximum, the eigenvalues of the graph we'd use would not be singular in this sense. We could simply work with the temporally lead category on the nose. We could write down this functor, this representation. Sigma would now be would be something like a quantum polynomial ring. There'd be no upper bound. We wouldn't have this restriction here. We really would build a causal resolution, and then we could drop almost from all of these statements. So this is very much somehow the other side of the dichotomy, the same dichotomy that the sum described. So I mean, the ADE case has this finiteness about it. In the general case, everything works a little bit better, and you can drop the almost here. So I should, as this is supposed to be about higher stuff, I should try to go higher and say something about the SU3. Okay, so in principle, if we have the SU3 version of the story, the same things, at least as far as I understand, the same three things about the conformal field theory are still true, the corresponding Witten model. The fusion category C now has doubly indexed simples, Vij, Ij positive and some less than k. Okay, so now it's generated by maybe I'll write V for V1 naught and V star for V naught 1 corresponding to the two dual fundamental representations. And now if I write down the fusion quiver for the fusion graph, I probably should say k equals 2 case, I obtain this sort of triangular quiver that very conveniently is exactly the same thing. I'm going to write down. So this is the fusion graph of truncated SU3 fusion so far, but we might imagine that it's also going to play the role of, indeed, as Thomas said. There is a A-type algebra which we wouldn't have to be associated with this, and we would hope we would see that. And we do. So then in the CFT context, you could try to ask what sort of representations do you see, or what sort of quivers might you expect to see. And this was written down originally by Francesco and Zuber. Inspired, if I understand it a little better, by both looking for non-negative integer representations and consulting Terry's Gannon's classification of the modular invariants for SU3. So in this case, the modular invariant story is there's a complete list of those, and then what the exercise they set themselves was. Try to write down a plausible list of quivers, which provides some of the features here, and the list. So the list is here, or this is half the list. Roughly speaking, so they classified the quivers still into sort of roughly A, D, and E types, but they're a little bit more complicated than that. But you see, the A types, at least we would plausibly recognize if we take this one as. So the first A-type family is the sum wrote down. The second A-type family is like the normal A-type family, but with some loops attached to the vertices, which some people sometimes like to do. And then the D-types are essentially obtained by orbifolding the A-types. And then there are some other ones which can't be generated in quite such a simple way, which are the E-types. And there's, roughly speaking, 3 families. There are 3 different Coxeter numbers that can appear. There's still a Coxeter number you can associate to these as the sort of root of unity, that telling you the root of unity of the eigenvalues. Powers of, so there are still exponents, and you can compare these with modular invariants. And you can also ask, do these quivers generate sets of matrices which represent SU3 fusion? You do. But then you can ask, can I categorify that? So can I actually get some sort of representation of the category, the right fusion category which underlies this? And the answer is not quite. You have to rule out the one which in any case has a question mark here. I guess maybe Terry can confirm. That one didn't have a modular invariant plausibly, or was there at least one you could plausibly attach to it? Or you don't know. Okay, so anyway, so apart from this one, this is now the list. So how do we see we see this? Well, it's kind of a lot more elaborate than the SU2 case. Fortunately, some people work very hard. So there is a diagram realization of C by Cooper-Berg spider diagrams. Okay, and the difference here is we do something similar to PL, except we have 2 sorts of dots really on interval corresponding to the 2 fundamental representations. We have oriented edges, so we might have a diagram like this, but now this is oriented, and maybe the convention is that it has to go. The black dot, the arrow has to come out of, and the white dot, the arrow goes into. So these are sort of particles and antiparticles in some strange sense. And there are equi-oriented triple points. We can also have diagrams like this. This isn't a dot, it's a triple point. And the only rule is the orientations have to be all outgoing or all ingoing. And then there are some relations. This should be 3. There's a relation. I'm not going to draw the orientation, so I'm just doing it quick here. I think this is effectively, apart from the isotopic relations. Something like that. I hope I've got that right. Okay, and then so in principle there's a similar story with idempotence. So this is the analog of TL. This should be a version of TL tilde, the quotient, which is semi-simple. This won't be semi-simple. Q is root of unity, and we'd like to make a representation of this category. So in order to do that, this diagram effectively is an expression of the duality between the two fundamental representations, but as before, in order to get the isotopic relations and this relation, it has to be scaled by some eigenvector with eigenvalue 3q. So there are some nasty scale factors around. And then there is possibly the simplest thing to say is there is this diagram. Is something which it's sometimes called an Occhianu cell in this context, but in other algebra contexts is now just called a potential or superpotential, which is a sum over the triangles in the diagram or some weights to do this triangle times the composite of the edges around the triangle. And of course we have the opposite orientation, so we also have a dual superpotential on the dual graph. And that's something which is possibly a little bit unusual from the representation theory point of view. Okay, and then, I mean, it's really a, I guess, Occhianu claimed that this is what you should look for. Well, obviously, because somehow you should be trying to look for this sort of representation, and maybe you could do this, and Guy, Adams, and Matthew Pugh really sort of roll up their sleeves and show you could do this. Indeed, in all cases on this list, except this one, shouldn't be on the list, in fact. So, like optimize yourselves for potential. W, of course, really is two potentials, W and W check, exist. sounds like it's unique. I don't mean that. Okay, so that means in this context, the data that you have somehow is you have a quiver. So you have the quiver, which essentially is the SS bimodule that's associated to this. So this is a U1. It's not a double in any sense. It's not supposed to be self-dual. In fact, the opposite quiver is the opposite quiver essentially tells you how you should represent the other dots, and then the duality between them is here, and on each of these quivers you have actually a superpotential, some weighted sum of triangles that appear in the diagram. So where are the algebras? Well, again, similar to before, in C there exist two graded algebras, or possibly not. Possibly not quite. Which essentially are the analogues of the polynomial ring. Just the sum of the symmetric powers of the fundamental representation. But it's possibly worth emphasizing here, and also, I don't know what to call it. I won't call it anything. I mean, there is a doubly graded algebra as well, which somehow has these two algebras on its two edges, so it's more like the homogeneous coordinate ring of the flag manifold instead of projective space. I think thinking more about what this algebra is and what role it might play is almost certainly a worthwhile exercise. It's really, as I say, I want to emphasize the fact that what we have in this context is really two quivers very closely related with two superpotentials which are very closely related. These relations, if you really put orientations on them, you'll see they effectively do involve both of the superpotentials and represent some sort of compatibility condition between the two superpotentials here, and this is some sort of closed condition I'll try to think of along the lines of the equation, say, xy equals 1. Distinguish it from, say, the open condition, x is non-zero, which you'd have if you had only 1. So this is a sort of closed condition which might reasonably impose some sort of natural genericity, open condition, on one of the two superpotentials. Okay, so finally, what else have we got as well as these graded algebras? Well, we've got their almost causal duals. So lambda equals v naught naught plus 1 naught v naught naught. V. Naught naught, this is in degrees 0, 1, 2, 3. Similarly for lambda check with just the two middle things. Reversed, and now the kind of interesting data here the interesting parts of the co-multiplication are from lambda 2 to lambda 1 into lambda 1 as before. So now this would look like this diagram. So this explains how the arrows of the dual quiver encode quadratic relations on the original quiver, and this is exactly the way in which you use a superpotential to write down Jacobian relations. And then of course there's also the duality in this case. Which in a sense is how superpotential gets turned into a relation. So there's a tiny co-algebra here, which really is exactly the one that one would write down in this context of superpotential algebra. And again, we have the duality here. Now, lambda is self-dual, but shifted by 3. So we're expecting a CY3 phenomenon. And so sigma check, and after we apply the let me not write down the shortest sequence. So it's a little bit more work to get from the SU3 fusion rules to a statement which is only made about these particular pieces of the representation theory, but you can write down three-term short exact sequences built out that are kind of derived from the fusion rules, and see that these algebras are set are almost comodules of these and so on. So inside C and sort of outside in the real world, where these are almost pre-Calabi-Yau algebras, which is what I was supposed to explain. So, thanks.
Any questions, comments? Yeah.
So, Okeana went on to do the issue 4 case and issue 5, if I remember. Have you checked those at all?
I haven't. You have to be quite, yes, strong to start doing that. But I mean, certainly from what one would have to speculate that those lists will give rise to things that are of a similar nature that Simon was telling us before. I mean, the basic, the regular representation is exactly this higher simplex, higher preprojective algebra that he wrote down this morning. So, but I mean, I certainly haven't thought about this directly myself.
So what does this buy you, looking at it in terms of preprojective things? I mean, these things were sort of understood in the context beforehand, so...
in some sense, I'm not exactly sure where I'm standing and where I'm looking, but part of I suppose the challenge here is for the representation theory community to say there is a sense in which this list, I mean, we can understand this list in some other context. I mean, that would be somehow almost the ideal situation. I don't know whether that's maybe unrealistic. I mean, as I tried to emphasize, there are some aspects of this that are kind of familiar, the superpotentials and Jacobi algebras and things, and some aspects that are a little bit unfamiliar, namely having these two dual guys which are in some sense compatible. So, I mean, I don't really know.
So what you would like is to have some kind of representation theory where you would actually land exactly on this list for other reasons.
Exactly so, yes. Yeah. That's sort of a real challenge for the representation theorists. Whether they can say something that you didn't know already in the conformal field theory context or the fusion category context, it's not clear, maybe. One would have to know, I guess, what questions you might like asked, if there are any questions that are left. I mean, perhaps for me, well, I don't know, For me, one question still, which I mean we are working on a little bit, is how do you understand the modular invariant? I still think there's a question to be answered there, but that's another thing.
One question I'm interested in is so each quiver contains some potential.
Yes.
And I'm wondering this potential have a cut or perfect matching.
I imagine so. I mean, after your talk this morning, I suppose it would be natural just to try and say these sort of things. If you do cut them, will give you fundamental algebras for which these will be higher preprojective. But presumably this happens a lot. In some sense, I mean, this list is unlikely to be picked out by that requirement alone, but possibly these. I mean, that's certainly what one should like. All of these should be higher preprojective. I mean, that would be a very natural conjecture. But which ones?
Very short question.
Really short question. So you say almost 3 Calabi-Yau algebra. Is there a definition of almost 3 Calabi-Yau algebra?
Yes. I mean, it was implicit
Implicit.
in the example. So there was this co-algebra, which is self-dual in this way. That's the 3 Calabi-Yau is almost a causal dual.
Okay, I think I understand now. And so this is true for all the monoidal functors F.
It's true for all the algebras you get by applying F to
For every F, for every monoidal F.
Yes.
Yeah. And so can you give me a very simple example of what F of sigma might be? Because I've got no feeling for it.
Maybe we should postpone that because we have no break anyway, right? We're already 5 minutes late, right? Okay.
I mean, this is just to say one sentence. It is the Jacobi algebra of these quivers with the potentials that you get by writing down the right weights, which you have to ask Shai and Matthew for, on the triangles on these pictures.
All right, thank you. Let's think on this again.